Okay, good morning. I'm going to present this work about concolic testing in logic programming. So this is joint work with friend Mesnard and Étienne Payet from the University of Rhode Island. And well, let me start by briefly introducing what concolic testing is in general. Actually, this is a very popular technique in the imperative and object-oriented programming languages. You can find a number of tools like Java Pathfinder, Qt and JQt, CLI, and so on, that are well known and quite mature, and you can use these tools, for instance, for test case generation. This is one of the main applications, but not the only one. They can also be used for debugging and some sort of model checking, so these are very useful tools. And well, our plan is to develop similar tool but for the case of logic programming. So let me start by briefly introducing the basic approach, which is only based on symbolic execution, the basic approach to test case generation. So here we start with an initial call to our program, say main, with a couple of parameters, x and y, and an initial environment in which x is bound to a symbolic variable, which is shown in red, and the same for y. So we don't have concrete values here. This is just symbolic execution. Configuration is a triple of this form. So we have, say, a program location, an environment, and a constraint, which is called a path condition. Basically, the idea is that this path condition represents the constraints that should hold in order for the concrete computation to reach this point. Okay, for the initial values to reach this point. So initially, the path condition is true, which means that this configuration is always reachable. Then, say, we perform some step and consider, for instance, that at this point we have a conditional like this one. Then, since the current path condition is true, it means we have no constraint on x and y. We can follow both branches. So in any of the branches, in the first branch, we update the path condition to x greater than 0 with a new constraint, and in the else branch, we update the path condition with x less than or equal to 0. Okay, so this is basically the idea. Whenever we find a branching point where we can follow different paths, then we just update, we consider all of them, and we just update the path condition with the corresponding constraints. Okay, so let us consider that the tree is already finished. So usually this symbolic execution tree might be infinite. This is quite usual, but we must stop the construction of the tree at some point. Okay, we can different heuristics for that, but every strategy is in principle sound. So here we're interested in a form of soundness. Soundness here means that basically means that if we have a state here, this state should be reachable. Okay, so if we find some constraint, some path condition, and we don't know whether this path condition, this constraint is satisfiable, we should stop this branch of the tree. Okay, the idea is to ensure that whenever we reach a configuration, by solving the constraints, we get values for x and y such that a concrete execution with these values will actually reach this program point in the execution. Okay, so this is basic property of this technique. So what's the idea? Once we have finished the construction of the tree, we should produce the test cases. So for that, we only need to solve the constraints in the leaves of this tree. So we had two leaves, this one and this one, and by solving the constraints, for instance, we might get two test cases like these ones here. So what's the point? By executing main 2.0, we are sure we will reach this point. And by executing the other goal, the other initial call, main -1,1, we know that we will reach this point here. Okay, so that's why the test cases generated by symbolic execution usually achieve a very good program coverage. So what are the drawbacks of this approach? So the main drawbacks is that when you define a symbolic execution mechanism, sometimes it's very difficult to deal with some program constructs. So higher order calls when the function name is a symbolic variable, so you don't know which function to call, and well, you can perform some closure analysis. There are some ways to improve the situation, but this is not easy to deal with. And there are a number of other program constructs like built-ins, input-output concurrency, and so on that might be difficult to deal with symbolically. The same, this is perhaps the main problem. We might get some complex constraints, and it might be the case that the constraint solver is not able to prove satisfiability of these constraints. So what can we do at this point? As I mentioned before, the only sound way to proceed is to stop the symbolic execution, since we want to ensure that any configuration, that any program point that we reach in the symbolic execution should actually be reachable in a concrete execution. So we don't want to explore, we don't want to have false positives, or we don't want to explore an execution space which is not reachable. And the consequence of that is that we might get a poor coverage by stopping the computations whenever we are not able to prove whether the constraint is solvable or not, is satisfiable or not. So as an alternative to symbolic execution, it was defined some 10 years ago, the notion of concolic execution. So in concolic execution, we start with both a concrete and a symbolic initial call, as you can see here. So this is an initial concrete initial call. Might be randomly generated or provided by the user. It doesn't really matter which one is the initial call. So you have this environment here where parameter x is 1, parameter y is 0 in this case. And again, we have an initial symbolic call as before, okay, where we have symbolic variables. So now a configuration has an additional component, which is the concrete environment. And the difference with respect to the approach based on symbolic execution is that in concolic execution, the symbolic execution part just follows the same steps of the concrete execution. That is, at this point here, we look at the concrete execution, at the concrete values of x and y. So since x is greater than 0, according to this environment here, we will only follow the then branch. But it's the same for the symbolic execution part, okay, even if x and y are not constrained, okay? So in some way we have one concrete execution and one symbolic execution in parallel that only follows the same steps of the concrete execution. That's the main difference, okay? So we don't construct all the tree, we don't follow all the possibilities, but we only follow the same branches, the same selections of the concrete execution, okay? So this is just one single computation. So what are the advantages? On the one hand, well, control is easier here because we know the path to follow in symbolic execution, which is the same of the concrete execution. That usually makes the process much easier. And moreover, in case of difficult program constructs, or in case of constraints that we don't know if they are solvable, if they are satisfiable or not, in these cases, we can always use the concrete values, okay? Because we know the concrete values of every variable. So by using some concrete values, we might simplify, for instance, a constraint so that we can prove that it's satisfiable, okay? And this is always sound. I mean, if we can prove by providing some concrete data that the constraint is satisfiable, the original constraint was satisfiable too, therefore this is sound. Okay. Well, but there's something missing. So we have one concrete execution together with a symbolic execution, and now what? So how do we compute new test cases? So for that, what we should consider basically is the computed sequence of constraints. Okay, and for each sequence, we should negate the last one, and in this way, by solving these constraints, we will get new values for the input data, so that we have a new concrete initial call and again a concrete execution with the associated symbolic execution and so on. So this is sort of iterative process. Okay, so for instance, in this concolic execution that I shown before, by negating this constraint, okay, we get, for instance, this value. So we get a new concrete initial call, and given this sequence, by negating the last constraint, we get again values, for instance x equals 2 and y equals 42, so we get a new concrete goal that can be used again to repeat the process. Okay, so this sort of iterative algorithm. Okay, so what about logic programming? So on the one hand, there are some good news. This is that in this paradigm, concrete and symbolic execution are the same, so we don't need to introduce a new semantics, a new mechanism for symbolic execution. That's really nice. That's a very good advantage. But there are also some bad news. So on the one hand, this is the language introduces non-determinism and backtracking. This is something well, something a little bit we should be careful with that, and actually we will consider semantics, which is not the usual one, as I will mention later. On the second hand, so things are not so simple as in the imperative case. So there we have a conditional, and if we enter the then branch, the alternative is clear, it's entering the else branch, so we just need to negate the condition of the conditional statement. What about a logic program? When we unfold an atom, what are the alternatives? So that's not so immediate, and I will look at that later. And finally, some basic, very basic properties of concolic execution in imperative languages no longer hold here. So for instance, if we consider that our language is not pure logic programming but also includes operators like cut or negation, it might be the case that we have an execution, a concrete execution or a symbolic execution actually, that succeeds with some bindings, okay, computing some bindings, and if we back propagate these bindings to the initial goal, this goal follows a completely different execution path. Okay, so consider, for instance, let me show you an example. So for instance, this program, okay, so this program is a very simple logic program. The only thing that is not pure logic programming is this cut operator here in blue. Okay, and well, if we call this program, let me load the program, we call p of x, we get a solution, x equals b. It's actually the only solution, but if we execute p of b, the program enters an infinite loop. So it's not following the same steps of the symbolic execution. And actually, this is something that is assumed here. Okay, when we follow this concolic execution, we expect that by solving the constraints, we will get values that will reach this point. Okay, and this is not true anymore in logic programming. So we should be careful when defining a concolic testing tool for logic programming. Okay, let's move now to the technical details of the paper. So let's start with the concrete semantics. So as I mentioned before, we are not using the usual semantics based only on SLD resolution, but we are using this linear semantics introduced by these guys, well, a variant of this linear semantics introduced by these guys at Lobster 11. So in this semantics, a state has this form here. So a state is a sequence of goals where each goal is labeled with an answer, a substitution, with the bindings computed so far. Okay, and well, intuitively, this sequence of goals denote the leaves of the SLD tree built so far. Okay, so this is basically the idea. Well, we only consider initial atomic goals of this form labeled with the identity substitution. And okay, the main difference with the original linear semantics is that we only consider the computation of the first answer. And well, let me explain why we changed the original semantics in this way. So the reason is that we consider that in real practice, when we have realistic product programs, usually the programmer is only interested in the first answer for the initial goal. This is so first goal is sort of main, and if we have some backtracking, we are interested in some non-deterministic predicates. These are not the initial goal. These are somehow hidden in the execution of this program. So that's the reason why OS semantics only considers the first answer for the initial goal, okay? Because if we consider the semantics in which all the answers are considered, we might get the impression that with this goal we are achieving a very good coverage, and that is not the case. So in order to have a fair notion of coverage, we decided to change the semantics to only compute the first answer. Okay, that's more or less the reason. So here you have the rules of the semantics. These first three rules are very simple. We have the first goal in the sequence if is true, then we have a successful computation. As I have just mentioned, we forget about the other possibilities, so we don't compute all the solutions, just the first one. If we have a failing goal and there are no more alternatives in the sequence, then this is just definitely a finite failure. And if we have a failing goal but there are some alternatives, so this sequence is not empty, then we just perform a backtracking step, which means removing this leftmost goal from the sequence. Okay. So this is the main difference with the standard semantics. So in order to perform an unfolding step, we have so we do it in two stages. So first we apply this choice rule. So whenever we want to unfold this goal here, and this is the selected atom A, so we look for the clauses that match this atom. But what we do in this first choice step is to duplicate this selected goal as many times as clauses we have here, and we label each copy with the corresponding clause, C1, C2, and so on. Okay? And well, choice fail is just a particular case in which there are no matching clauses, so we just replace the selected goal with fail, and then we might apply failure or backtrack. And finally, we have goal with some label, some clause labeling the goal, and well, as usual, we compute the most general unifier between H and between A and H1 and so on. Okay, this is just a standard folding step. So let's start with this initial call to P of f of x with identity substitution. So first we have a choice step. We have just one copy because this atom here just only unifies with the head of the third clause. Therefore we only have this one copy of the initial goal. Then we can perform an unfolding step as usual. So we get R of x here, still labeled with identity substitution. Now we have another choice step. In this case, R of x unifies with both R of A and R of C. Therefore, we have two copies of the selected goal, R of x, with the corresponding clauses. Now we have an unfolding step for the leftmost one. So we have some true here, successful computation, and the computed binding is x equal A. And now we apply a success step and the computation terminates, and as I mentioned before, this goal is just discarded. Okay. Let's move to concolic execution. So it's a very simple extension of the concrete semantics. So the main difference is that now in a state we have two goals, or much better, two sequences of goals. The first sequence of goals is the sequence of concrete goals, and the second sequence is the sequence of symbolic goals. But actually they are all acceptable goals in logic programming. Okay, it's just the only difference is that the concrete goals are usually more instantiated than the symbolic goals. That's all. Okay, so now the initial state has this form. So we have an initial goal which is provided by the user or randomly generated, and then we have a symbolic goal which has the same predicate but just fresh variables as arguments. Okay, and well, these are the rules of the concolic execution that I'm not going to explain. So I just want to mention because the extension is actually it's not difficult. So you can find the details in the paper, but I just want to mention a couple of details. So the first one is that when we perform a choice step, okay, so this is A, the atom, the concrete atom that I want to unfold, and this is A prime, which is the symbolic version of this atom. Usually A prime is more general than A, which means that A prime might unify with more clauses than A, okay. But anyway, we only follow the same steps here in the symbolic part. We only unfold this atom with the same clauses matching the concrete goal. Okay, so if the concrete goal matches with clauses C1, Cn, this is exactly the only clauses that I'm going to consider for unfolding the symbolic atom, even if it matches with more clauses. Okay, the same idea as in the case of imperative programming. So symbolic execution should follow exactly the same steps of the concrete execution, right? And the second difference, with the second point I want to mention, is that we label this step with this pair of list of labels. So the first element here is a list, a sequence with the labels of the closest matching the concrete goal, okay, the labels of C1, Cn. And the second element here is a sequence with the labels of the closest matching the symbolic atom. Usually this is a superset of this set here, okay, or this is a bigger sequence. Okay, these are sets, so this set is usually a superset of this one, okay, because the symbolic atom is more general, right? So for choice fail is just a particular case where there are no matching clauses for the concrete atom, so the first set is always empty, but the second one might be non-empty, okay? So that's what the only details I wanted to mention. This is the same example as before, but now we have a concolic execution. So this is the concrete goal, and this is the initial symbolic goal, P of a fresh variable, say n. So we have a choice step as before, and we compute these two sets. The first set just contains L3, the label of the third clause, which is the only clause matching P of f of x. But the second set in this choice step is this L'1, in which we consider the labels of all these three clauses, because P of n matches with all of them. Okay? So then we have an unfolding step, another choice step, and I'm going to show you all the details. Actually, you can find this example in the paper. Okay? So let's start with the test case generation. So what do we do with this concolic execution? Concolic execution. What do we do with that? So we should look for alternatives, and this is different from what it's a little bit more complex from what is usually done in imperative programming. So whenever we have a choice step label like this one, as in the example, what are the alternatives? So basically the alternatives are all the possibilities with these three clauses, okay, the clauses that matched the symbolic goal, except for this one, this selection, that is the one that we have already considered in this particular concrete execution. So what are the alternatives? So the alternatives are matching no clause, matching only the first clause, matching only the second clause, matching only the third clause is discarded because it's already there. So matching only the first and the second clauses, matching only the first and the third clauses, and so on. So basically the power set of the matching clauses with the symbolic goal, and then we have to remove the particular selection of the concrete execution. Okay? So for instance, so it doesn't mean that all these alternatives are feasible. So for instance, given this P of x and all these three clauses or heads of the clauses, not all these alternatives are feasible. So for instance, matching no rule is possible by binding x to b, so that P of b does not unify with any of these atoms here. But matching only the first clause is not possible, because whenever we bind this variable x with some value so that it matches p of s of a, it will also match the second clause. Therefore, matching only the first clause is not possible. We can provide values so that it only matches the second clause, for instance p of s of b, and so on. So, but look that some of the cases are actually infeasible. Okay? So, in order to check whether one of these alternatives is feasible or not, we have this algorithm. So it's a unification problem that you can find in the paper. So basically it's like that. So we have an atom and we have two sets of labels. One set L, which represents the clauses I want A to unify with the head of these clauses, and another set L prime, which represent the clauses I don't want to unify with. Okay, so for instance, if we one problem could be an atom A, P of X, and then one set of labels L1 I want to match with, and then the second set would be L2, L3, the clauses, the labels of the clauses I don't want to unify with. Okay, so whenever I have a problem like this one, so it can be represented in this way. So we are looking for a substitution, okay, such that A unifies, this is what this relation represents, A unifies with the heads of the clauses labeled with labels from L, and I want A theta to not unify with the heads of the clauses in the set L prime. Okay? But this is not as simple as it might look like, because this is not equality, this is unification. So actually, if you want to replace unification with equality, this is the actual constraint. So we are looking for a substitution such that there are substitutions sigma 1, sigma n, such that all these equalities hold. And moreover, for all other substitutions, sigma n plus 1, sigma m, these equalities do not hold. Okay, so it's sort of second order unification problem. Okay, so it's not so simple, and when you can find in the paper a constructive algorithm that implements that solves this problem. Okay, and checks the feasibility of the different alternatives. So this is the algorithm for concolic testing. I'm not going to show you the details. I think it's might look complex, but it's more or less the same that is done in other in the imperative paradigm, so it's not particularly surprising. So we have to select one atom from this set pending. So the next test case to consider a concrete goal. So we perform a concolic execution for this selected atom. Then, we compute a trace associated to each concolic execution. This trace is useful to avoid exploring the same space many times. And then we compute all the possible alternatives for this concolic execution, so that we produce new test cases that are added to the set pending, and the process is repeated until the set is empty. So this is typical iterative algorithm that you can find in any in concolic testing for other paradigms, and you can find the details in the paper. Well, finally, I would like to mention to show a little bit about how it works in practice. Actually, we have developed a tool for concolic testing in Prolog, which is called Contest. So, this is the URL of where you can find a web interface to check how it works. If you write down 2 here, then this is not the stable version. This is our ongoing working version with some extensions that are not completely checked so far. So let me show you a little bit how it works. Okay, so this is the tool. You can write down a program, a logic program here. You can also select one of this list. So this is the simple program that I showed before in the slides. Okay, so in this first box we can write the initial atomic goal, any random initial atomic goal. It doesn't really affect too much to the process. So this is the where we write down the list of arguments that should be ground. So in this case, the only argument should be ground. This is the types of the initial call. Uni stands from universal, which means that we are providing no additional information. It means that the algorithm, that the Concolic testing tool should infer the right types for the argument automatically from the program. So any term is fine here. The maximum term depth is used in order to avoid generating. So when we have function symbols, we can construct infinitely large terms. So this number, this 2, is used to bound the number of the size of the terms that we are producing. We also have a bound for the SLD3. This is actually not required when we deal with terms, but it's essential when we deal with integers, for instance. And finally, we have a timeout in order to ensure that if the process takes too much, we just stop the algorithm, the Concolic testing procedure. Okay, so we can. You press start. These are the test cases that we are producing. So you can check the traces of these test cases. So a trace means a sequence of choice steps, and each choice step is represented by the set of the matching clauses. Okay, so you can also check this box. So it shows what are the missing clause labels. So in this case, we have that the first clause of predicate Q is not covered by these test cases, and the reason is that it's not reachable, because if we call P with P of S of A, so that Q of A is called here, so we enter the first clause, but we never reach the second clause. And if we call P with P of S of, say, B, then we enter the second clause, but it will not match with Q of A. So it's not possible to reach Q of A. Okay. And well, you can also check which ones of these test cases are actually finite failures. So by checking this box here, you get this asterisk here, which identifies P of C as a finite failure. Okay. Well, things are not always so simple. If you have many clauses defining a predicate, you might get so remember that the alternatives were a power set of the number of matching clauses. Therefore, this kind of programs might take a lot of time to produce the test cases, because we have to check many alternatives. And well, this is something we are working on in order, we want to improve, we are improving right now. Okay, so this example shows the usefulness of types. So you write here the default types, universal types, then we get the test cases which are not so useful, like this one, where we have a list of an empty list of another empty list and things like that. So by providing types, we can reduce the search, the domain of the terms we are generating. Okay, so making the process more efficient, but moreover, so it's faster actually, but moreover, the test cases are more useful. Okay, are more reasonable. Finally, let me show you one example with dealing with integers. So this one, computing the factorial of a number. So well, you can also use a cat operator and things like that. So we start the process, we get these test cases with a full coverage. Okay, but the nice thing is that we can also say exchange these two variables. So this is a bug that is not detected when loading in the program in a prolog environment. Okay, because every variable occurs at least more than once in this clause, so we get no warning at all. But if we start the process, we get a number of errors here. Okay, that comes from the incorrect instantiation when evaluating is. Okay, so our tool can be used. So we get the error, we get the initial call, and we get the erroneous call. Okay, so this kind of tools, as I mentioned at the very beginning of this presentation, can be very powerful and useful debugging debugging tools. Okay. So, well, you can find in the paper some experimental results with this tool. Well, they are quite satisfactory. We get almost full coverage in all the examples, and in the remaining examples we get something between 80 and 90% of the coverage. So these are quite good results. So as a future work, well, we want our tool to be larger, faster, and cheaper. So we want it to be applicable as many features of Prolog as possible. We want it to run as fast as possible while it's still ensuring soundness, of course. And we'd like to get very good coverage for the sets of test cases that we produce. So, and some ideas we are currently working on. So on the one hand, the use of types, as I mentioned in the web input interface of our tool. But let me say that we are only considering types for the initial goal. So we don't need type declarations for each predicate. We don't need a type inference algorithm. This is just types for the initial goal, because this piece of information is very useful to reduce the domain of terms that we are producing. And also, our algorithm, the bottleneck, currently the bottleneck of our algorithm is the checking the feasibility of all the alternatives. As I mentioned before, that we have to compute the power set of the matching clauses, and this represents really a large set of alternatives. And we have checked that many of these alternatives are actually unfeasible statically, so we don't really need to check that during Concolic execution. So we plan to define some static analysis to rule out as many alternatives as possible statically. And finally, we are currently using a ICLP'15 constraint solver from Prolog, and it would be nice to use more powerful constraint solver, not only for integers but also for reals, for strings, for terms, and so on. Okay. Well, that's it. And if you have any questions, you can write to me an email, and I would be very pleased to answer your questions. Thanks.